Hi, I'm Kobayashi from Sony.
In this video, I will explain the most popular configuration of Recurrent Neural Networks LSTM long short-term memory without using mathematical expressions. This video is aimed at those who have an understanding of the basics of neural networks and recurrent neural networks, so please refer to the playlist of Introduction to Deep Learning and the video What are Recurrent Neural Networks in the video description section. Let's start with a brief review of RNN, Recurrent Neural Networks. The RNN was a neural network with a structure in which the output of one time step becomes the input of one next time step, with feedback from the output side to the input side in time series data. As shown in this figure, it can also be expressed as feed-forward neural networks by expanding it in the time direction, that is, in the horizontal direction. In this case, the network at each time step is the same network with shared parameters. RNN has such a structure that it can realize processing such as classification in consideration of time series while inheriting the past information. When expressing RNN as feed-forward neural networks by expanding it in the time direction, it becomes quite complicated, especially in the structure of LSTM, which I will explain in this video. Therefore, I would like to explain in this video how to express RNN using the neural network console. Here, RNN expanded in the time direction on the left, and the expression using the neural network console on the right represent the same network. In the neural network console, you can express RNN expanded in the time direction in a compact and intuitive way. To explain in more detail, the network on the left-hand side will have data input from each input layer at each time step. On the other hand, in the network on the right-hand side, data for all time steps and data for multiple time steps are input at the input layer simultaneously. In this way, the input data of multiple time steps will be cut out one by recurrent input and output to the network at a later stage. For each time step data output from recurrent input, the processing from recurrent input to the subsequent recurrent output is performed every time step in common. Also, through this delay, the output of the past time step will be carried over to the next time step. More concretely, the first time step data is extracted from the multiple time step data input from recurrent input, and in this case, the concatenate, affine, and tanh processes are performed. The data processed by tanh will be carried over to the next time step through delay. At the next time step, concatenate, affine, and tanh will be processed in the same manner for the data at the second time step extracted by recurrent input, and the result is passed on to the next time step through delay as well. When the processing of all time steps is done, the result of the processing at each time step is simultaneously output to recurrent output. Since the network on the left-hand side uses only the output of the last time step and not the results of the processing except for the last time step, the network on the right-hand side is configured to extract only the output of the last time step using the slice layer. Thus, the neural network console enables to express the structure of RNN like this, in the form close to a schematic diagram. Now, I would like to briefly explain LSTM using this notation method. The simplest RNN structure described in the video What are Recurrent Neural Networks is called Elman-net or simple RNN. Each time step is processed by one layer of affine, linear transformation and activation function only, and what is passed on to the next time step is the computation result of each time step itself. In contrast, LSTM is structured like this. LSTM, compared to Elman-net, has such a configuration that it is possible to retain long-term memory even when the time series becomes long. At the same time, it provides more stable training than Elman-net. At first glance, it may seem rather complicated. I will explain the role of this structure one by one. Once you know it, it's not so complicated, so you don't have to worry about it. One change from Elman-net is that this LSTM has 3 additional gates in addition to affine and tang H, which were also in Elman-net. In Elman-net, only the hidden state of each computation result is carried over to the next time step, but in LSTM, in addition to this, information called cell state is carried over to the next time step. Now, I will explain the structure of LSTM. I would like to improve the structure of LSTM little by little from the structure of Elman-net. Elman-net combines the output of the previous time step with the input of each time step, performs linear transformation and applies activation function with affine and tang H, and then passes the result on to the next time step. One of the weaknesses of Elman-net is that the information passed on to the next time step is rewritten every time step by affine and tang H processes. For example, if information dozens of time steps ago has a significant impact on the results, deploying it in feed-forward neural networks requires that the results be retained even after dozens of layers of processing. However, in Elman-net, this information is rewritten every time affine and tang H are processed, which makes it very difficult to retain long-term memory. Therefore, we add a mechanism called cell state to store long-term memory. This cell state continues to add up the output of Elman-net every time step. Specifically, the output of the first time step is added to the initial time step, and the result is transmitted to the next time step. And then the output of the second time step is added to the output of the first time step, and the result is transmitted to the next time step. This process is repeated every time step. In Elman-net, the output hidden state of each time step is rewritten, but by adding the cell state that adds up the time steps without rewriting the result, it is possible to retain the long-term memory. In the video, The Mechanism of Neural Network Training, I explained the batch gradient descent method and backpropagation. In backpropagation, when this addition process is differentiated by the input and becomes 1, the gradient that comes back from the process at the subsequent time step is multiplied by 1, that is, it propagates as it is to the previous time step. In other words, the addition of the results of all time steps has the great advantage that the gradient of each time step propagates directly to the previous time step, thus stabilizing the training. By this mechanism, in Elman-net, the gradient would backpropagate through the long feed-forward neural networks expanded in time, but in LSTM, the gradient at each time step would propagate as it is to the previous time step. In the video Multilayer Techniques for Neural Network, I introduced a technique called Residual Networks, which does not use time series but achieves multi-layer training with a similar effect. Now, it is possible to retain long-term memory compared to Elman-net, but there is still a problem. At this stage, cell state is updated by adding the output of Elman-net each time. Therefore, we can say that it is a structure in which the memory is gradually rewritten when the time series becomes long. As the next step, we will introduce a mechanism called input gate. Input gate has a functionality that selectively takes in input and determines whether to input or not depending on the content of the input. Specifically, input gate is affine and sigmoid, that is, a linear transformation and an activation function, which produces a value from 0.0 to 1.0 for each neuron, as shown here. Then the value of each neuron 0.0 to 1.0 is multiplied by the result of affine and tang H using Mul2, which is processed as the Adversarial product for each element. We can understand that the 0.0 to 1.0 values output in affine and sigmoid represent gate, which opens or closes the gate to enter the data. If the input gate is 0, that is, if the gate is closed, the output will be 0 regardless of the value of the output of affine and tang H, which means that nothing will be added to the cell state. If the input gate is 1, that is, if the gate is open, the output of affine and tang H will be output as it is and added to the cell state. In other words, The input gate determines whether the data input by affine sigmoid should be stored or not, and if it should be stored, opens the gate and stores it in the cell state, or if it should not, closes the gate and retains the previous cell state value. We add a gate to the output side as well as the input side. This is called output gate. It works the same way as the input gate, using affine and sigmoid to create a value from 0.0 to 1.0 to indicate on and off of the output, and then multiplying the value by the output at each time step for each element. The output gate will output the value only when it should be output, or output the value weighted from 0.0 to 1.0 as applicable. The output weighted by the output gate will be the output of the LSTM itself, and it will be carried over to the next time step through this path that has existed in Elman-net. In other words, the output gate controls the information that is passed on to the next time step, so that information that is useful for the next time step is passed through. But information that is not useful or has a negative impact on the next time step is not passed through. And finally, we add another gate called forget gate. In previous networks, cell state values were always adding up. However, the past memories are not always good to keep forever, and sometimes it's better to forget information that seems to be no longer needed. For example, if the input sentence is, "Yesterday was sunny," no, it wasn't, it was raining. It is better to forget the information that yesterday was sunny when you say, "No, it wasn't." Forget gate, for example, achieves this kind of functionality. In the same manner as the other gates, create a value between 0.0 and 1.0 for each neuron in affine sigmoid and multiply the value by the cell state value at each time step for each element. This enables to retain the cell state value when the gate is open at 1.0 and to forget the stored cell state value when the gate is closed at 0.0. Thus, LSTM uses cell state in three gates, input, forget, and output, to retain long-term memory. In other words, selectively memorize the memory according to the situation, selectively transmit it to the next time step, and selectively output it. That is why the structure of the RNN allows for high performance and stable trading, especially for problems that require long-term memory. I hope you were able to understand the structure of LSTM. I have included links to sample projects of Elman-net and LSTM using the Neural Network console in the description section of the video. The RNN sample project using the Neural Network console is a sample of guessing handwritten numbers by inputting MNIST handwritten digit images one line at a time from the top as if they were time series data. Intuitively, you are shown the image one line at a time as shown here, and you are solving the problem of guessing what number it is. For those who are interested in it, please run it and check its performance yourself. Furthermore, as I explained in this video, I think it is interesting to see the performance while gradually transforming from Elman-net to LSTM. You can also use convolution instead of affine, tweak the LSTM structure further, and try other RNN structures such as GRU with ease in the Neural Network console. Because of the complexity of recurrent neural networks, many people use the structure of RNN or LSTM as it is, but please try various weights and structures if you like, then I think you will be able to understand RNN better.